my series around. Well, welcome back from our little intermission. Now we're going to go through the soil orders of Canada. So this is a map, and the soil orders seem to make sense based on habitats, right? So the cryosolic ones are all up in the Arctic where there's permafrost. The podsolic are all in the boreal forests of the Canada Shield. The Chernozoic are all in the prairies, etc., etc. So we'll go through exactly how all these soils are formed. One of the first, most important and oldest soils that have ever been classified are prairie soils. They have different classification names in the States and in Russia, but they are one of the first soils because these are the ones that humans have been using. The word Chernozemic comes from the Russian soil classification system. Their dominant feature is that they have high levels of organic matter formed from the roots of grasses. And we'll talk about this. A lot of grasses senesce in the winter, and when they lose that green material on the surface, they also shed some of their root material underneath and create soil. Pretty like prairies have an amazingly thick black humus layer from this creation of soils. So we typically see a large AH. So you can see this is your topsoil, and then you have a large AH section. Sometimes you'll see AP for pasture, so those are human disrupted soils, and E for alluviation. At the bottom of your H layer, you might have an alluviated A layer as well, which is what you're seeing down here, some alluviation. These soils typically are rich in calcium. These are great soils for cropland. So here's another example with a larger alluviation layer. And then this is the map where we're going to see these Chernozemic soils. Mollisol is the term they use in the States. And we have them in varying degrees of color difference, where we have really black Chernozems, dark brown, and then light brown. And I don't know if any of you have ever been to the prairies, but this section in Saskatchewan and Manitoba that is black Chernozem is super black. Like the kind of topsoil you buy from the store black. I couldn't believe how dark it was when I went to Manitoba for the very first time. This is the actual diagnostics of what soil you have. How do you know you have a Chernozemic soil? These are the exact instructions for classification. I don't want to go through them all because the odds of you guys having a Chernozemic soil is pretty slim, but I wanted you to have this information in case you were interested in knowing about it. So there it is for you. And here is the official Soil Orders of Canada map. I'm going to include the map for each soil. As you can see, it's almost exclusively in the prairies. They are grassland soils. Solonesic is another grassland soil, but this one is lacking that AH layer. Its defining feature are the clays and sodium levels. So you can see the BNT, N for sodium, Na is sodium, T for ton, the German word for clay. So the soils don't look quite as dark, and you're seeing like a smoother material from that clay enrichment and that lighter color from that sodium enrichment. They're definitely a very different color than the Chernozemic. So again, here are the diagnostics, and they're much more rare. They're specific places in the prairies. So again, prairie soils, but under specific conditions. Podzolic are the first of our forest soils. And this is the one that we typically see, the most common one in our area. They are found in coniferous forests with sandy material that's been on igneous rock, which describes the bedrock. We have our bedrock, which is igneous, and we had glacial till on top. So this is a really common soil. So it's defined by their B layers. The diagnostic is a BF or BH layer, where we have that humus is leached down through the soil column. So you get these oxidized BF layers. You frequently see these AE layers are quite striking in podzols. And then you sometimes also have these humic BH and AH layers. So here are the diagnostics for podzols. We will probably look at these quite specifically because they have measurements about when you have a BF or a BH, exactly what is happening. Because when you're subgrouping from a podzol into a ferrohumic or a humoferric, it really, matters what the percentage is of humus to oxidization. But we'll look at that more specifically when we're actually digging our soil pits. Here's a map of podzols, which very closely follows the lines of igneous rock. So we have them along the Canadian Shield. We have them in the old mountain ranges that go through here and the newer mountain ranges that go through here. These are igneous rocks that have sandy soils on top and then dominated by conifer forests because they're in northern or colder climates. Luvasolic is another forest soil. This one includes some more loamy, so that AH layer is more important. And then instead of a BH or BF layer, we have a BT layer. So we have more clay coming down. And that's why this H layer is more loamy. Loamy is a mixture of clay and sand and silt. Whereas podzolic soils tend to be dominated by clays, or podzols are dominated by sands. Luvisols are dominated by slightly more clay-like soils. So we're looking for where's textural contrast. So there's a textural contrast between here and here. Whereas with the podzols, it's less texture contrast and more color contrast. So again, the colors are not quite as distinctive, but the textures would be. And here's our map. So again, we're looking at forest soils, but now here, where is this? This is the clay belt. I don't know if you guys knew this existed, but like New Liskeard is here, and this is all farmland in northern Quebec up here. So I assume the other places are smaller clay belts as well. Southern Ontario, again, limestone soils, limestone forests. Brunasolic is our third forest soil, and this one's a little bit harder to ID. It's typically a transition soil. So if you don't have the distinctive horizon layers that you have in some of the other ones, then often it's a brunasolic. It's less weathered, it's younger. And we have a BM layer. So we'll talk again more about the differences between podzols and brunasols when we look at our soil profile, because there are some brunasols in our area. But as you can see, they're more common in the north than down here. And I think they've just spent less time unglaciated, so they've had less time to form. Glacials are one of the easy ones. The dominant feature is glade. So they've been saturated for most of their life as a soil. So you're getting glade B layers as well as glade C layers because the water saturation is all the way through. And you're going to find them in low-lying areas where you can get high water tables. Regosolic is where there is no B horizon. So this is usually where there's conditions where pedogenic conditions aren't happening. So they're frequent where there's like unstable slopes or very little organic matter. Like I was talking those alvar fields sometimes. But you can see in this particular, where'd my pen go? You can see in this particular picture here, like this is all just the sand. And you've got this tiny little B layer at the top, A layer at the top. Like there's pretty much just sand and then organic matter on top of it. And same here. Like it's just all sand and then some little bit of humus on the top. So there's a tiny little B layer here between, but realistically, the majority of the soil is that unconsolidated, untouched C layer. So some gravel pits, you might see a soil like this. On alvars, you see soils like this sometimes. So not super common. Vertisols are fun. This is the defining feature of vertisols are Slickenslides. This is another German thing. That SS stands for Slickenslides. So what has happened is when you have a lot of clay, you'll get these hardening of the soil and then a crack, like this crack here and this crack here. Those cracks are called Slickenslides. And because it's a clay, the water will slip down and make these edges smooth. So as the clay dries out, it'll shrink, and then as it grows, it'll expand, and you'll get these cracks where water slides down, and you'll get mixing between the two horizons. So it means that your A horizon and your B horizon, you'll have these weird cracks where the mixing goes up and down these lines, and there's less defining horizontal lines. So this very specific, you need to have those Slickenslides. So it's a very specific condition for vertic soil. And as you can see, they're pretty rare. We're getting to the easy ones. Cryosolic, literally it has either been disturbed from the processes of freezing and thawing, or it is currently frozen. That's it, cryosolic soils. They're pretty easy to spot. And we don't have any in North Bay, obviously. We're not in the permafrost. Obviously, the maps just of the Arctic, where there's permafrost. Organic soils are when we have accumulation of organic material, usually in a wet area, mostly made of peat or muck. This is a really common in the dips of the boreal forest. So defining feature of a lot of the boreal forest in Canada are these rocky soils, rocky substrate where you get these dips and you'll get isolated and palustrine wetlands. And organic material has a lot of time to form and sort of get stuck in those lowlands. And you can get some pretty old organic soils. And there's no mineral content because the glaciers scraped all the mineral content out of there years before the organic content started to accumulate. And if you have mineral soil, they're really deep. And we have a few of these on campus that I bring my students to. You might find one. They're often in small little pockets. Or depending on how big your lowland areas, you can have large, like in the Great Lakes, St. Lawrence lowlands, there's some pot patches, and in the Hudson Bay lowland, there's a lot of it. I was just saying. So Hudson Bay lowlands, a lot of organic soil. But even anywhere throughout that boreal where you have those little pockets of organic in between our podzol forest soils. So we've just gone through the orders. So now we're going to look a little bit at great groups and subgroups. So I actually have a key. This is like a screen capture of my key for the great groups. And the great groups are looking at properties that reflect the strengths of those major properties. So the orders, for example, the glaisolic order, the dominant process of all glacials is that it's been saturated underwater. It has glaying. But a secondary process in that glaying might be that there's clay translocation. Clay translocation is the main feature of a luvasol. So you might have a luvic glacial, which is what this says underneath my face over here. Or if there's a really giant AH horizon in your glacial, you might have a humic glacial. So the great group is just an additional qualification of a secondary feature. So the main overwhelming feature is that it's glade, but it also happens to have this secondary feature. And this is why we have ferric podzols and humopodzols and humoferric podzols. Is your podzol mostly full of humus, or is it mostly full of oxidized iron? The subgroups are now looking at additional features. So our orders were the main pedogenic process. Our great groups are secondary processes that are still important. The subgroups are now looking at additional special features. So they usually start, where'd my pen go? Oh, it's upside down. That's why it's not working. So orthic is just, they're showing this is the median. This is your standard. So an orthic gray luvasol is your typical gray luvasol. And then a dark gray luvasol is showing intergrades with the chernozemic order. So then it has a large, our dark one is going to have a large AH layer probably. This says O, which means it's probably the orthic one. But that's basically the key identifier of chernozemic has a dark AH layer. A podzolic is going to be a gley luvasol that is showing some podzolic traits, but like it's not a secondary trait, it's just an additional trait. So I was going to guess, oh, this says PZ, but I would guess this was podzol because of this AE BT layer thing happening in here. So the subgroups are less important, but they're something that when you're trying to describe a soil down to its series, which we'll get to shortly, is important. For our purposes of this class, we'll probably just do our orders and great groups, but some of you might have an orthic classic example where it's really easy to name the subgroup. So if you can, please do, but totally understand if your sample is difficult. Families, we start adding all these little tiny features. So is the soil clay or is it sandy? Is it a cold weather soil or a warm weather soil? And you can really start to add a lot of defining features, and families are where we start naming our series. Specifically in this family, we have this named series and this named series. And this is far from what I want to focus on in this more introductory to soil science course. If any of you decide to go into soil science, you'll learn how to do this much more detailed way. So within the families, we have series. So you can't sample an entire series, but you can sample pedons in the landscape And then if the pedon continues to have that same family distinction, you can then collect up a bunch of pedon samples and have a series. So a series is like a member of the family. Specifically, me and my brothers and sisters, we're all very similar, but we're all each have our own specific qualifications that make us each a different person. So each soil family have specific series within them. So this is an example here. The Paxton series is one that's near university and is well documented. So yeah, here is the state of Massachusetts, right? And here's the Paxton soil series. So it's quite a large soil series. So every time they do soil sampling and they find another soil, like they probably didn't have this one originally as part of the soil series, it's probably been added as they sample more pedons, and they're like, hey, this pedon has all the same series qualifications as the Paxton series. So it has very specific features in their horizons, and they probably have specific measurements of the horizons as well. So summing up, right? We're going to learn how to get to order. That's the main pedogenic process. And then we're hopefully going to get to great group. So that's a secondary pedogenic process. For some of us, we might be able to get to subgroup. So those are transformative features. And then I'm not expecting us to figure out exactly what family, but it's good to start noting these fine features. And then right now we're going to look at a couple of different series. Soil pit. I don't know why I have a picture of a soil pit. This is where we come to soil survey. Here is a soil survey map. So we have several of these maps on campus that we can look at a paper copy. I have a full version of this. It's a huge file so that you can zoom right in, and if you want it, let me know and I will share it with you. They're made by the government, so I totally feel fine sharing them. But I'm going to, like, this is Trout Lake for those people who aren't from North Bay. So the campus is up here. And my house that I grew up in is here. So here we go. Here's our campus, right? Canada College. And our soil pits are going to be in this yellow area. So this yellow area, and maybe we might have some in this pink area. We used to go across the street, so we'd be in this beige area as well. But these letters and codes stand for different soil series. So each of these different colors on this screen are representing different soil families, and the letter codes are different series within those families. Oh, I forgot I'd added animations. I'm usually doing this at school on a screen. I don't have a pen and a tablet to draw with. Okay, so here is the legend that shows you all of those different series and families. So for example, these are the two that I circled on the map. And this is showing you the order, the grape group, and the subgroup, right? So it's a podzol, it's a humopheric podzol, so that's the grape group, and it's specifically an orthic humopheric podzol. And both of them, if you look down here, this one is also an orthic humopheric podzol. So what makes them different? So over here, we have our family distinctions. These are the different surface textures and soil materials that are really specific to the family. So we're not looking at the processes that form it. So the order, grape group, subgroup are the processes. The family distinctions are the traits, the physical traits of that soil, so texture and materials. And you can see here This one's formed sandy loam on glacial till, Precambrian origin of the soil monolith beneath. And this one is slightly different. Gravelly sand outwash of Precambrian origin. So we're missing that loamy glacial till part. Coarse sand down here, not loamy till. And here's our series distinction. So this is specifically what makes it that series and not a different series. So each one of these is going to be slightly different for each of these soils. And we don't need to go into all the different distinctions of the soil. This column here is the column that I am caring about for our purposes. And maybe a little bit of these too. And then lastly, here's the series name. So each color has a different series name. And typically each family of colors is a family. So remember, the family have different series in them. So on campus, we have the Monteagle and the Wendigo, which are kind of fun series names. They're usually named after areas. So like there's a Wendigo Lake locally that it was probably named after. I'm not sure where the Monteagle came from, but I'm assuming there's probably a lake or a township name that's Monteagle somewhere, because this series might not just be local to North Bay. This series might extend quite far. Right? So we got lots of different ones on our map. Now, all of this information probably just went whew, right over your head. To get it to cement into your brain, you really need to go and dig a soil pit, which is why it's such an important part of the course and why I've been racking my brain trying to figure out ways for you guys to do this. I'm going to film some videos of different soil pits around campus and give you guys some hints of how to look at soil profiles out in the wild. And we have an assignment where I want you guys to actually draw out a soil profile and describe it and classify it. Because really that's the only way to get a handle on all of this terminology, is to work with it, right? Like trying to memorize the periodic table is impossible, but when you start working with those chemicals, you start to memorize certain features of them. The more you work with something, the easier it is to remember things. We're not going to make any soil monoliths, but I've given you a bunch of websites, or I will in the next slide, and those websites have soil monoliths. So I wanted to explain exactly what they are. When someone names a soil series, they frequently create a monolith that they then keep in like a museum or university as the sample of that soil. So other people can refer to that monolith when trying to identify their series as the same series. So you have to dig a really big soil pit. We're probably not going to dig more than a meter deep. And it's typically you would build a soil pit that's a meter by a meter by a meter. We might not do that because this is just one small project in a term. But if you were making a soil monolith, you'd need to definitely go more than a meter deep, and it would have to be wide enough to give you room to fit in a wooden box and cut around it so that you can sort of slide your wooden box in and then cut down so your soil profile falls into your box. And then you bring it back to the lab and you clean it so it looks beautiful and all the features are neat and tidy and not blending. And then you preserve it. So this is done traditionally with waxes. Now we use resins and epoxies, but it's preserved in a way so that the color stays. Because once you've cut into that profile, you lose all those colors. Any oxidization and reduction that had happened in that soil naturally is going to occur from the oxygen in the air. Any moisture that's giving color to that soil is going to get lost or gained. So by filling it with some kind of a resin or a wax, you preserve those moisture and color features. And all the monolith pictures that I have in this PowerPoint and on the websites online are all created in a similar fashion. So these are the website I was talking about. We've got, this one shows a bunch of soil monoliths from the UBC website. This one is the official Soils of Canada website. So a lot of the So a lot of the information that I've given you, especially the diagnostic tools, are from this one. This is a good mapping website for those of you who like ArcGIS and mapping. And this one has our specific orders and great groups for Ontario with monoliths and diagnostic features. So they're good resources to have, and hopefully they'll help you when you go to do your soil profile. See you soon.